Right, so without further ado, again, thank you for joining us on our. Just admit someone else. Can you just carry on admitting if you don't mind? So again, thank you for joining us on our Lunch and Learn webinar series. This is the first of our webinar series. We have more that will be coming on over the next 3 or 4 months. The next one will be next Friday on the 14th of July, and we're going to be extending this session by taking an in-depth look into the TA-Slider and the digital configuration of the TA-Slider itself. So essentially what we can do with it, what tools we have within the digital configuration of those actuators, and how we can best utilize those in our systems. So for this one, we are going to talk about our TA-Modulator for modulating control. So an evolution of the TA-Modulator. Originally, we start with the TBV-CMP. So that was our first pressure independent control valve that was introduced in 2009. From this, we grew into the TA-Compact P, which was introduced in 2014. Both actuators are linear actuators. So both of these will deliver 20% flow for 20% of the lift. And they have what's called a linear characteristic. This evolved to the TA-Modulator, which has an equal percentage characteristic. Typically, linear characteristic valves will have an equal percentage characteristic built in within the actuator that controls it. We do the opposite. So our TA-Modulator has the EQM control within the valve, and we use a linear operation on the actuator. With digital configuration, we can actually use this actuator with our Compact P and change that characteristic to suit. But for modulator purposes, we just need a linear control characteristic. So pressure handling. If we look at the available differential pressures for our TA-Modulator, certainly with the small ones, so starting with our DN15 and 20, we look at a minimum differential pressure of 15 kPa to a maximum differential pressure of 400 kPa. The DN25 and the DN32, we require a minimum of 25 kPa. So this is the minimum amount of differential pressure required to operate the valve. And then again, a maximum of 400 kPa. Our P1 pressures, which is our incoming pressure, our delta H. So this is the amount of available pressure coming into the valve from the system, acts on our control port. So our P2 pressure is going to react and start to close as the P1 increases, or as it decreases, it will open up. The backside of that, we have our P3 pressure. So our P3 is going to interact on the other side of the face of the diaphragm, and this is where we will create an equilibrium across the valve to maintain a constant differential across the control plug, which allows us then to deliver accurate flows at each setting. Delta H, which is the amount of differential pressure, or the minimum amount of differential pressure we need to operate the valve, is from front to back of the valve, so effectively our P1 to P3 pressures. We can measure flow by plugging into our test points, our high pressure and low pressure test points, and we can measure P2 and P3 pressures across the control plug, and this will give us our calculated flow rate across the valve. We can also measure the available differential pressure onto the valve by measuring between our P1 and P3 pressures. So here we still utilise the high pressure and low pressure terminals, test points on the top of the valve, but we bypass part of the valve. I'll show you in a little bit more detail later how we actually go about doing that. So why are we talking about modulating control? The TA-Modulator has been developed to work together with our IMI which is our thermoelectric actuator. So this is typically a wax actuator that heats up and then starts to operate. And then our TA-Slider actuator, which is our digitally configurable electromotive actuator. Typical applications, as can be seen, are fan coil units, air handling units, chill beams, plate heat exchangers. And it's recommended in applications where we want to control the power in proportional to the load conditions throughout the system. So where do we get this overall circuit characteristic from? Our terminal characteristic, or our thermal efficiency of our terminal unit, say our fan coil, for instance, will have a specific thermal efficiency and a characteristic that relates to that thermal efficiency. Typically, we tend to see this type of curve on heat output coils for fan coils, for air handling units, very generic terminal units throughout our systems. Our valve characteristic, in our TA-Modulator's case, slightly different. But we're looking at an equal percentage characteristic, which is almost the mirror of our heat output coil curve. Other influence on the system is obviously our DP variations, our hydronic network itself. So changes throughout the system are going to affect how well we can perform and how well we can control. Typically with control valves, we look for good authority, and the authority is measured as a ratio between the differential pressure of the valve being fully open and at design flow over the differential pressure that's being measured across the valve when it's fully shut. This gives a ratio figure that allows you to give an authority to the valve itself. Then our actuator characteristic also adds on to our circuit characteristic. So in this instance, we want an EQM characteristic valve and we want a linear characteristic for an actuator. Typically what you see in most valves and what you would see on our previous iterations is a linear characteristic on the valve, and we would compensate that with an EQM characteristic in the actuator itself to try and give us the best level of control possible with an equal percentage characteristic available. And the target is to give us a linearity between the power output and the control of the valve itself. So if we want 50% of the valve open, we want 50% of the power. Touching on authority, the lower the authority, the larger the DP variations on the control valve, the larger the distortion of the characteristic of that valve. So the bigger the distortion of the controllability of that valve in effect. So here we can see we have our lift versus power and our linearity between the two, which is our perfect system linearity that we want to achieve, which would be a level authority of 1. Realistically, when we're talking about pressure independent control valves, a lot of people will talk about pressure independent balancing and control valves having an authority of 1. Due to the way these valves work, they have to see a change in the differential pressure to actually operate and to be able to move. That change cannot be predicted by the valve. It has to see that change first. So the authority of 1 is not achievable with a pressure independent control valve. But you can, however, achieve an authority of 0.7 and above. This will vary due to the variations in the system itself, how much differential pressure we have, how much flow we have through the valve at the time, and the type of control that we're doing. So it will vary. We can see the lowest acceptable value is 0.25. So on control valves, we always look for 0.25. On our graph, we can see that that's quite distorted compared to our perfect linearity between lift and power. But it's nowhere near as bad as the characteristic that we can see for anything below 0.25. So a characteristic of 0.1, we're almost pushing our characteristic back the same as the terminal unit itself. So we're almost matching the terminal unit, which is going to give us a very poor control. Anything in the excellent band, which is 0.5 to 1, as I say, we won't go there, but 1's not really achievable. But anything above 0.5 will give us this excellent bandwidth. So we can see we're in a very tight control compared to the perfect linearity. So the curve is actually very slightly distorted, but it's as close as we can possibly get it. So theoretically, the goal is an EQM with a thermal efficiency of 0.25. So our coefficient A corresponds to the thermal efficiency. And most commonly in heating and cooling temperature regimes, they will have a thermal efficiency of 0.2 to 0.4. There are certain instances where plate heat exchangers, things like that, will actually have a higher temperature thermal efficiency. They will be at 0.7, but typically for fan coils and terminal units, we will be between 0.2 and 0.4. Also, with the trend on temperature regimes is to have a larger delta T, which also leads to progressively higher thermal efficiencies. And as we can see in the graph, we have our perfect EQM at 0.25, which is just behind the blue line. And we have our EQM at 0.2 and an EQM at 0.4. So we can see this is typically the bandwidth that we want to be operating in. And with our valves at 100% open, 40% open and 20% open, and with an EQM set at 0.27, we can actually see that we are as close as possible to these control widths that we want to be at. Why does this happen? So when we're talking about a TA modulator having an EQM characteristic, the reason being is the control plug that sits within the valve is a small control plug here is actually what gives us the equal percentage characteristic across the pressure independent control valve itself. So why move? Why create a valve that does this? Well, as we can see, comparing our TA modulator now against our original iteration, the TBVCMP, and also the Compact P, which will have slightly less distortion because it's a newer valve, but originally compared to the original TBVCMP, it will still have its distortion of control. Whereas as we can see with lift linear, we get a very tight control bandwidth available through the TA modulator being set at an equal percentage. Typically, most manufacturers will go down this route with a linear valve, and we can see that type of linear valve with the actuator compensating for the equal percentage still gives us a very large distortion on the control itself. So hence the reason why we go down the TA modulator route to have the equal percentage in the valve. For a theoretical purpose, if we look at those two different scenarios as an EQM valve versus a linear valve, our global system characteristics are going to be pretty much the same as we will see. So our actuator characteristic on an EQM valve will be linear, whereas our actuator characteristic for a linear valve will be equal percentage, as can be seen. So then we add our valve in. So we have our EQM valve and our linear valve. With our hydronic piping and our DP variations from the system, and then our terminal unit characteristics, effectively, we should have a global circuit characteristic, which pretty much matches each other. Both have a very small distortion compared to a perfect linearity, which on paper looks fantastic. However, this is not quite the case when we're talking about linear valves. But typically for a system, for 50% of the heating season, we are going to be at 20% of the flow. If we look at that compared to flow versus power, 50% of the power output is actually at 20% of the flow. So 80% of the year, we are going to be sitting at this point or less. And as you can see from the graph itself, this is such a steep curve to achieve from 0 to 50% across only 20% of the valve's lift, whereas the rest of the other 50% is actually controlled by the other 80% of the lift within the valve. If we're sitting this for most of the year, you can see that controlling low flows and being able to control as finite as possible is key to achieving good system control and good temperature control for our rooms and our buildings. We compare the two types of valves. If we look at a new characteristic, so our EQM characteristic of our TA modulator, against that of a linear valve. So we could use our TBV CMP or other manufacturers' linear valves. We can look at how we can control still delivering that 50% power output at 20% flow. So if we set both valves to 100% open, we will typically get this type of graph. So this is our equal percentage on the valve. This is our linear percentage on the valve for our linear valves. So for 50% of the power output, again, we're at 20% flow. If we look at the EQM valves, at 20% flow on our characteristic, we are just below 60% of the maximum lift. So we still have 58, 59% of the lift available, which, as you can see below, interprets to 0 to 2.4 millimeters of stroke. Now, on a smaller valve, a 15 millimeter valve, we will tend to have 4 millimeters of stroke available. So setting that valve down to 20% of the flow, going to be our maximum stroke available is still 2.4 millimeters. If we then compare that to 20% of the flow through a linear valve, which is only now at 20% of the lift, we only actually have 0 to 0.45 millimeters of stroke available, which is quite small. If we then further regulate that valve, so we go to 40% of our maximum design flow through the valve. Again, our characteristic comes down, we hit our 20% of the flow, and we are just below 40%, so 37% of the maximum lift available, somewhere around there. So we still have between 0 and 1.5 millimeters of stroke available to control these lower flows past 20%, to still control that 50% to 0% power output of the coil. Whereas if we look at that versus a linear valve, we still only have 0.18 millimeters of stroke available, which is very tiny. We reduce that even more. So we take now our maximum flow rate to 20% of the maximum flow rate permissible through the valve. When we hit that 20% mark again, we still have 0.9 millimeters of stroke available on a modulating valve. Whereas opposed to a linear valve, we're now at 0.09 millimeters of stroke. So we are less than 5% open, and we have a very tiny window to operate between, and we're still trying to control 50% and lower of that power output with those valves. So as you can see, we still may have 5 volts available on a 0 to 10 volt actuator that is still going to try to control those very small flow rates. And through a linear valve, EQM will struggle because the amount of stroke available is just too tiny. If we graph that out and we look at it, we can see that we have this very finite curve that still goes very, very low with an equal percentage valve and a linear actuator, as opposed to a linear valve with an equal percentage curve or an equal percentage characteristic. We can see that setting 20% of the valve maximum flow rate, we are just below 40% of the lift. So yeah, we have no control available, but we still have voltage supplied to the actuator. So we still theoretically should be able to control to those lower flows below 50%. Only once we've gone past 40 or 37, wherever that may lie, we are no longer able to control those flow rates. And with a setting at 40%, again, slightly better, but it's still not perfect, and it's still not as close to 0 as possible. So the question is then, are we actually modulating, or does the valve just literally become on-off past a certain point? So how does the valve work? When we look at the DP controller, this compensates for variations of available differential. So as I said, our P1 pressure is coming in. This is changing constantly, so it's increasing or decreasing. So as it increases or decreases, the diaphragm within internal of the valve is going to adjust to counter those increases. How do we set the valve? So for adjusting we'll talk a little bit more on the next one with digital configuration, because we can set these valves mechanically by the hand wheel. There is also a method for setting these valves digitally, so we don't actually have to move the hand wheel at all. We can leave the hand wheel at setting 10, which is how it comes out of factory, and we can limit the stroke availability to match the flow rate and actually set accurately flow rate through the valve with the actuator. As I say, if you want to join us next week, we'll talk about that in more depth. But setting the valve mechanically, we're going to turn the hand wheel. So we'll turn that to our desired position, and that will adjust the control plug itself. As we do this, the DP controller, as you can see, will act simultaneously. And when the actuator starts working and closing and opening to a partial load, both working in a simultaneous way to achieve our flow rate across the valve. Just to show you our technical parameters, the functionality of the valve we control with an EQM characteristic, as we've discussed. We can do flow limitation, DP control, because we're balancing and controlling our differential pressure with the diaphragm internally. We can also measure flow, temperature, and our delta H, so our available differential pressure through the valve. We can also shut the valve off as well. So there's a position on the smaller valves, which is +1, which is called position X. We can move that and fully isolate the valve. On the slightly larger valves, which we'll see shortly, there is just an operation to 0, but I'll cover those in a while. Again, our characteristic is equal percentage. Our flow rates through the valve, so the DN15 unfortunately is in litres per hour, because most of our products are made in Europe, so everything is easier slightly in litres per hour as it is into litres per second from a visual purpose. So 92 to 480 litres per hour permittable through the smaller valves, up to 720 to 3,600 litres per hour through the 32mm valves. We have a leakage flow, so that is all control valves will have a leakage rate. So the leakage flow is actually equal or less than 0.01% of the maximum flow rate permitted through the valve. Our differential pressures, again, we're at a maximum of 400 kPa, and then our DPV minimum is 15 kPa on the 15 to 20. And 25 kPa on the 25 to 32. The smaller valves are male threaded, so they actually come with a G thread, and we have a drip-free closing for maintenance, and the temperature range is typically 0 to 90 degrees. We do have an alternative which goes up to 600 kPa and is allowed permissible for temperatures between -10 and 120 degrees. I'll touch on that slightly later. So actuators, as I said, we have our IMI TM, which fits, and our TA-Modulator, which fits IMI TM for operating our 15 and 20mm modulators, and then our Slider 160, which actually covers the whole 15 to 32mm range. Once we go past that, we need a slightly bigger actuator, but we'll see those very shortly. And just some indication on the typical types of flow rates and settings that you can get, flow rates through each setting. When we tend to size valves, we typically try not to go to its extremity. We try and give a little bit of wiggle room between a maximum and minimum flow, so you have that room for manoeuvre. So if you're sizing your own valves, take that into consideration, because obviously your flow rates change. You may have a valve that will still be able to do a slightly higher flow rate just by adjusting the setting. Also check that it's within the working range of the system as well. So just make sure we're between that 15 to 400 or 25 to 400 kPa. So just some brief guidance on installing, setting up and how we do things. Say the TA-modulators are a male G thread. So this allows us to use our female threaded connections and our male threaded connections, which can be added on. We also have a welding connection, solder connection, and a connection for smooth end and press coupling. We also have a compression connection as well. And as the TA modulator is a G thread, it also allows a flexi hose to be able to fit it straight over the top of it, so the unit connection will fit flat face. From an installation point of view, Compact P and the modulator will take all three actuators, our IMO T, our IMO TM, our new TA-TRI, and our Slider 160. With regards to installation, if you're using the IMO TM or the Slider 160, we can configure this so we can actually orientate the valve in a 360, or we can hang the valve in any 360 orientation. So it will allow us to do that. With the larger valves, our Slider 750, we can't hang it directly down, but with the smaller valves, we can. We require a minimum 15 millimeters of free space above the actuator. This is so you can actually physically get the actuator off the top of the valve and onto the top of the valve. And as you can see, we also have the sizes of each different type of valve with the actuator added onto it, from a center to the top of the actuator purpose. So for installing, there is a flow direction arrow that's marked on the brass body itself, which can be seen just here, very small. So always make sure that the flow is following the direction of the arrow. With regards to fitting the valves onto the unit, we can fit the valve, the modulator and the Compact P onto the return or the supply pipe. Realistically, as long as the flow direction is respected, it doesn't matter. Typically, we tend to fit on the return, just purely from a point of view, we're at less risk of cavitation, because obviously our return temperatures are a lot lower than our flow temperatures, and it pushes us further away from the risk of cavitation on that lower temperature side. But in real terms, flow or return, it doesn't matter. So our operating function, again, if we're setting mechanically, we can turn the hand wheel to setting 5, and that's it. For a shut-off purpose, we go a clockwise turn past 1 to X, and that will completely isolate the valve. For measuring flow rate, if you're setting mechanically, typically we want to remove the actuator so we can allow the maximum position. So we've got no inference from the BMS. We connect our TA scope, which is our DP measuring tool, and we input on the scope the valve, what size it is, what the setting is, and then we take a DP measurement across that valve, and that allows the flow to be displayed. We also put the flow in, so it will give you a percentage of where you are in the system, how much flow you're actually achieving compared to your perfect design flow. For measuring delta H, which is our incoming pressure, as we say, we wanted 15 kPa as a minimum differential pressure onto the 15 and 20 mil valves. To measure that, we remove the actuator again, and we close the valve according to shut off. So we go to the X position and completely isolate the valve. Once that's done, we can open the high pressure test point, and we use a 5 mil Allen key, which is the red test point. So we place our 5 mil Allen key into the high pressure test point, and we do 1 turn anti-clockwise. This now bypasses part of the valve. It doesn't disengage the DP controller, but it bypasses to allow us to measure our P1 and P3. So effectively, we're measuring at 2 points rather than our P1 and P2 being, our P3 being influenced by the diaphragm itself. We connect the scope again, and we take a DP measurement, and that will give us our available head pressure. So it will show how much available pressure is coming from the system at that point in time. And again, important, just reopen the valve back to the previous setting if you're doing it mechanically. If you're doing it digitally, we would say go back to 10 and leave it at 10, and then place the actuator back on. If you're doing it mechanically, set it to setting 5 or setting 6, and close the bypass back. So put the Allen key back into the high pressure test point, and 1 clockwise turn to shut the bypass part of the valve and close the test point off. So to look at this from a system point of view, from an application side of it, if we were looking at manual balancing compared to the valves that we produce now, so the TA-Modulator and the Compact P, from a manual balancing system, where we want balancing and control, we would typically use our TBVC for an on-off purpose. So this is just a linear open and close valve. And for modulating purposes, we would use our TBVCM. These would go on each terminal unit, and then on the branches and on the risers, we would also do a balance for each branch and for each riser with a STAD or a staff, depending on the size of the pipe work. So we would completely manually balance the system. For pressure independent modules, where again, we're still using our TBVC for on-off on our terminal units, and we're using our TBVCM for our modulating on our terminal units. But we need to control our differential pressure because we're no longer a manual balance system. Our DP is varying throughout the system. So we need to control those DP variations to enable stable flow through each of those terminal units. Typically, we would do on the riser or on the branches a STAP or STAD. So this is our DP-CV and partner valve. So we control the DP through the STAP and STAD and allow the balance and control to be done through the TBVC and the TBVCM. With pressure independent balancing and control valves, typically on an on-off system, we would go with our Compact P. And for a modulating system, we would go with our TA-Modulator. On the riser, we actually wouldn't use anything. There's no need for any other balancing or form of balancing on risers or branches. What you can do in this instance, and what we would probably advise, is to still use a STAD or a staff, depending on the pipe sizes, for diagnostic purposes. So no, we're not regulating flow through those valves. Those valves stay fully open, but we can use those valves to record an accumulative flow. If you've got a system with 300 fan coils on one floor and you've got to just take a quick stab in to get an idea of where you are within the system, instead of measuring flow across 300 fan coils, we can use the STAD for diagnostic purposes to make sure we're achieving the flow rate we need to satisfy that circuit. We can also do, from a diagnostic point of view, again, delta H, so we can measure our available differential pressure through the STAD itself as well. So we can see that we've got enough differential pressure to satisfy that circuit as well. And as I said before, this is our smaller unit. It also has two larger brothers, one slightly larger brother, which is our DN40 to DN50, and then our very larger brother, which is the DN65 to 150 mil. So to cover the range for our DN15 and DN20, we have a 4mm stroke. To cover that 4mm stroke, we need a slider 160, an IMI TM or a TA-TRI. So the IMI TM is our thermoelectric actuator, as discussed before. These are the wax ones, which require warming up for 20 minutes or so before they actually start working from an initial point of view. And then the TA-TRI, which is an electromotive actuator, but it's our on-off and 3-point actuator. It's another alternative to 0 to 10. For our DN25 and 32, as discussed earlier, we still use the slider 160. So it's a 6.5mm stroke on the DN25 and the DN32, but the slider 160 can cope with both 4mm stroke and 6.5mm stroke. The DN40 and DN50, as we can see by the pin that's sticking out of the top of the valve, we have a 15mm stroke, which is quite large compared to its smaller brothers. So there we would need our next iteration of the TA-Slider, which is our TA-Slider 500. We can also use its slightly bigger brother or bigger sister, which is the TA-Slider 750. In order to mount the Slider 750 onto the 40mm and 50mm valve, we have to have an adapter. So the shoe on the bottom of the Slider 750 requires 2 bolts to be mounted, and the adapter allows the shoe to fit over the top of the valve and be bolted up correctly. As we can see from the next iteration, so the 65 to 125mm, We have 20 millimeters of stroke available on those valves. So we typically use our TA-Slider 750 and our TA-Slider 1250 to cover both ranges. We would typically use the 1250 over the 750 depending on your available pressure. So if your close-off pressure is very high, you might need more force to be able to close that valve down. So we would go to the 1250. Now, with the introduction of the 150 mil valve, we have 30 millimeters of stroke available, and we also have our new TA-Slider 1600, which will cover all of the stroke availability for the 150 mil valve itself. So just to touch on the setting mechanisms for both valves, for the 40 and the 50 mil, they look exactly the same as each other. This is our 0 turn, so we're fully closed. So we use the little orange hand wheel, and this turns and lifts the bar inside to show you where you are as an indicator between 0 and 2. And all of the 10th turns are on the orange hand wheel itself. So if we wanted 0.63, we'd go to past 0 and to 6 on the hand wheel, and past 6 to 6.3. And for 2 turns, we're just fully open to 2 and 0, and that would be completely open. For the slightly larger valve, we have the large orange hand wheel. The top indicator, which you can see on this, shows 3, and then the 10th of turns are below. So this is for setting 3.47 currently on this valve. If we want setting 5, we just open it to 5 and 0. Setting 3.5, we just slightly open that more, and so on and so forth. And to fully close both, we would 0 both valves. Pressure handling across the 40 to 50, very similar to the 15 to 20. The only difference realistically is the fact that we are doing we require slightly higher differential pressures. So we need 30 kPa as a minimum to operate the valve, and again with a maximum of 400 kPa. We can measure flow across our P1 and P2. So we're taking a flow measurement across both test plugs, and we can see what the flow is. For measuring delta H, again, we do P1 to P3. And this time we actually deactivate the DP controller within the valve itself. And if you refer to our instructions on the data sheet, it will show you how to deactivate those DP controllers. These also have a vent key, so you need to vent as well, just to make sure that you bleed the air before you take a delta H reading. For the slightly larger valve, we require a minimum of 30 kPa, but we can go to a maximum of 800 kPa. On the next couple of slides, we'll see that we have some slightly increased differential pressures as a minimum, and the maximum still goes to 800 kPa. We do some high flow versions of the valve, and the high flow versions require a slightly increased pressure, or minimum differential pressure, in order to operate. Again, we have our control plug, our P1 and P2 pressures. So our P2 is controlling against our incoming pressure, and the P3 pressure, which is on the back face of our DP controller, is going to move the DP controller between P2 and P3 to remain a constant across the control plug to allow us to deliver a flow at a specific setting. And exactly the same as the others, we measure by measuring across our red and blue high pressure, low pressure test points, our P1 and P2, and that will give us our calculated flow based on the differential pressure across the control plug itself. And measuring delta H is slightly different on this one. So we close the valve as we would close the others, but instead of measuring across the same test plugs, we have a secondary test plug, which is our black test plug. So we would measure across the red, our high pressure, and the black, which is effectively our low pressure, and we'd get our available pressure from these 2 points. Functionality, we're exactly the same as the smaller iterations. We still control with an EQM characteristic. We do flow limitation, DP control, we can measure flow, we can measure temperature, and we can measure our available pressure with all valves. We also have the shut-off function with both valves. These are slightly different because obviously with the 40 mil and the 150, or up to 150 as we can see, we can actually physically close the valve down to 0, which isolates the valve. Our maximum lift is, as again, 15 millimeters on the smaller valve, and then 20 up to 30 mil on the 150 mil valve. And I'll cover what differential pressures we can take on the next slide. Our connections are male threaded on the 40 and 50, and then obviously flanged connection PN16 for the 100 up to 100. Sorry, from the 65 up to 150. So our DP ranges, as you can see, we have our 15 and 20 and our 25 and 32 modulators, and we also have a 15 to 25. The difference between these two is the diaphragm itself. So we can actually take the 15, 20 to 32 with an A metal differential pressure controller built into the valve. So that allows us to go to 600 kPa, and it also allows us to go to 120 degrees. Typically on the standard valves, we will be the 15 to 25 or 15 to 32, where we are at 400 kPa and a 90-degree maximum temperature. This is because the diaphragm is a plastic rather than a fully A metal diaphragm that goes into the higher temp, higher pressure. 40 to 50, we're at 30 kPa and maximum of 400. And then, as I said, 65, exactly the same, a minimum differential of 30 up to 800 kPa. With our high flow versions on the DN 100 to 125, we require a minimum of 55 kPa. So we can see we need larger available pressure in order to deliver those larger flows. And then the same with the 150 mil. We need 60 kPa as a minimum, up to 800 kPa then as a max. Our flow ranges can be seen for our smallest valve to our highest valve. So we're going from 92 litres an hour to 190,000 litres an hour. And just to make a little bit more sense to everybody, that means at the moment we can go between 0.0255 litres per second up to a maximum of 52.77 litres per second. We are aware that below 0.025 litres per second, typically we have to go to our compact P, but we're addressing this. So hopefully within the range, we will have a smaller valve to be able to cope with lower flows than 0.0255 litres per second. Again, our actuators for both versions of the TA modulator are our TA-Slider 500 or the 750 with the adapter, and for the 65 to the 125, our TA-Slider 750 up to our 1600. Please excuse the MC 160, that shouldn't be there anymore. So for an introduction into our TA-Slider itself, typically with actuators, when you're out on site, you will see dip switches on standard actuators and jumpers. These tend to leave us only 10 to 12 binary choices. You need a large book to be able to go through each dip switch to be able to change something very simple. So if you want to change your 0 to 10 volt controlled actuator to a 10 to 0 volt controlled actuator, in order to do that reverse, you need to look at the manual to refer to which dip switch you need to either have up or down to be able to make those changes. With the TA-Slider, that goes out the window. So with Slider, we have the Slider itself, the TA dongle, and then the app. So we do everything with the app itself. All of the configurations or live configurations that we can adjust, we do with the app. And the TA dongle is our Bluetooth bridge between the app and the TA-Slider itself. We have virtually unlimited configurations. As you can see, we are above 200 settings 200 setting possibilities. This is ever increasing. So as the range gets larger and larger and we introduce more products, the amount of configurations that become available also exponentially increase as well. So to do what we can do with the TA-Slider, for adjusting that many dip switches, we would need a very, very, very long dip switch block, which also means we would need a very, very long actuator, which is obviously going to give you a nightmare on site to be able to set up, and could be very expensive to actually house that many dip switches to have that much control and functionality within the actuator itself. The dongle is our Bluetooth bridge, as I say. We have a micro USB connector, which allows us to plug into the actuator itself. We also have a micro USB connector for charging the unit itself. So there's a battery internally, and that allows us to power some actuators, which I'll talk about shortly. We also have 4 touch buttons on the dongle itself. So we have an up, a down, an auto button, and a configuration button. And I'll talk about these in a little bit more depth shortly. We also have 2 indicators. So we have a battery indicator. So this will go red or green, depending on how well the battery is performing. And we also have the activity. So if you are physically connected to that TA dongle, no one else can connect to it, but you can see that you're connecting to it, as the LED will go solid green. Our auto button, so to go from auto to manual mode and reversely, the green LED will show that we're in auto mode, and when it's in manual mode, we'll have a red LED shown. When auto mode is engaged, we cannot operate the buttons on the dongle itself, so we can't press up or down to drive the actuator. As in auto, it's actually listening to signals coming from the BMS itself, whereas in manual, we're allowed to do up and down functions, so we can physically drive the actuator itself. And as you can see from the up button and down button, they literally are one press. If we press them again, the actuator will stop, and the LEDs blink to show that that's in motion. If we hold the up and down buttons simultaneously, we can actually force a calibration. So we can force the actuator to calibrate against the valve itself. And while it's doing this, it will pulse or do a double pulse to show that it's calibrating. Once that's stopped, it will have calibrated the valve completely. The config valve actually allows us to push digital configurations to the actuator. I won't go too much into this because we're going to lead on with this in a little bit more detail next week, but just to show that there's a functionality there and it's available. And this is just an indication of the LEDs and what they mean as the dongle is performing and doing the work you expect it to do. So from electrical override function, even if the BMS or the actuators have no power from the BMS or we can't drive the BMS, we can connect the TA dongle and we can physically upload or go into manual mode, so we can operate the actuator and drive it fully open or drive it fully closed or somewhere in between. We can also then save our parameters onto each slider with the TA dongle. So the dongle will provide enough power to allow us to build a configuration and push that onto the actuator so we can set it to work exactly how we want it to. We can also do that on repeated systems. So where we've got multiple PICVs on, say, again, relying on a fan coil system. We've got 300 fan coils and they've all got the same amount of flow, all got the same required flow rate, sorry. We can upload one configuration onto the TA dongle itself and paste that configuration onto every actuator that requires that same amount of flow, and they will work exactly as expected. So just to give you an idea of briefly of what we can configure within the actuator itself, we can change our input signal. So we can do the proportions, 0 to 10, we can do 10 to 0, we can change the direction that actually works in. We can do a split range proportion. So this means between 0 and 4.5 volts, we can control from one BMS point the actuator on the heating. Say it's a fan coil and it's 2 valves. We can control the heating valve with that 0 to 4.5, and with the cooling, we can control that from the same BMS point between 5.5 and 10 volts. You can set it however you like within the app itself as how it will work, but we can split those voltages within each actuator to say you will operate between X and Y, and that's exactly what they'll do. So this can actually reduce some of the system cost by reducing the amount of BMS points required throughout the system. We can also, on certain actuators, change the output signal, so we can output to 4 to 20 or 0 to 20 milliamps. We can change the speed. We can change the stroke. So this is how we actually set flow through the valve. By picking the valves on the next one, we can see what our maximum and minimum flow rates are through that valve, and then we can set the stroke so we can deliver the amount of flow rate that we want through that valve specifically. We can also force calibration and change the characteristics. So as I said before, the Compact P is a linear valve. So out of the box, the characteristic is linear on the Slider 160. So we can then change that to an EQM so it works with the linear valve to give you as good as control as possible through a linear valve. We can also have binary inputs. So if you've got something like a binary input-output Slider 160, we can actually feed from the BMS a binary input, say from a window on an actuator on a window. So the window opens, it sends a signal, and that signal gets pushed to the slider that tells it to close because the window's open. So the room no longer requires heat, and it will shut the heating off, or however the application is. We also have relays, so we can do triggers from errors. So if there's an error on the valve, on the relay versions of the sliders, we can send a signal back to the BMS to say there is an error, the valve has gone into valve blockage protection, or it's in low power because the voltage being supplied to it has suddenly disappeared, or even something like the input signal. So our 0 to 10 volt input signal has dropped. This, with the relays, we can actually get triggers to see what has dropped. And we have various other settings throughout that can be played with. We also have an error list, so we can actually see the last 10 errors through the valve, through the actuator itself. This is cyclic, so as a new error comes in, the oldest one drops off, but it will give you a list of errors throughout the system that it's seen within the last 10. We can also output that as a PDF through the app itself, so you could send those to us and we could review if there's something wrong with the settings, or if there's something wrong with the actuator. We could review all of the settings that are placed across the actuator itself. HiTune is our configuration app. It's available on Android and iOS, Apple Store and Google Play. For iPhone, it requires iOS 15 or later, and Android thusly requires 4.3 or later. That may have changed because this is an older configuration, so the minimum requirements will be listed on the Play Store. It no longer looks like this, unfortunately. This is a slightly older presentation, but the screens are now updated and you get a lot of information from each. So just to give you a brief overview of the range itself, we have our Slider 160 and our Slider 500s, which are the first iterations of Slider. So that included our standard and then the Plus models. We also had the KNX, which had minimal functionality, so just as an input signal. And the Plus, then with the in and output relay and binary functions, so the I/O, and our KNX R24 with the relay built into the KNX. As the range evolved, we have the CO, which is our changeover. So the changeover can be used to connect the slider with the actuator of a 6-way valve, and it minimises the amount of wiring and setup that you have to do to control those 6-way valves. And then we also released our Modbus and backnet versions of the actuator with more advanced changeover and relay toggling features. And then in 2020, we reduced the fail-safe versions of Slider 160 and Slider 500, with one being the binary input and the R24 with the added R24 bistable relay. This actually introduced another 4 models, so the Slider 750s and the 1250s also saw a high and low voltage fail-safe version with all of the relays built in. So everything is included with the 2 versions of the Slider 750 and 1250. And that's done. So thank you very much for your time, and I really appreciate it.